In order to calculate sums or differences and products mod 6 or more generally mod n, essentially what we do is ignore multiples of 6 or multiples of n. So in this particular case here, 2137 plus 512, we can write 2137 as 6 times 356 plus 1, so that 2137 is equivalent to 1 mod 6, and similarly 512, because it's equal to 6 times 85 plus 2, is equivalent to 2 mod 6. Their sum is equivalent to 1 plus 2, which is 3 mod 6. And likewise, if we're multiplying these two, then again we have the 2137 is 6 times 356 plus 1, and 512 is 6 times 85 plus 2. So if we multiply, we're going to get 4 terms. This term times this term is certainly a multiple of 6. That's here. This term times 2 is again a multiple of 6. This times that, of course, is a multiple of 6. And finally, we have 1 times 2, which is just 2. 1 times 2 is equal to 2 mod 6. So the answer is 2 modulo 6. Now this is justified more generally by this following theorem here. All congruences are modulo n. And I'll give the proof in the next slide. But the statement is, if you have two numbers, a1 and a2, which are congruent, and b1 and b2, which are congruent, then a1 plus b1 will be congruent to a2 plus b2, and a1 minus b1 will be congruent to a2 minus b2, and their product, a1 b1, will be congruent to a2 b2. So from above, we have modulo 6 that 2137 is congruent to 1, 512 is congruent to 2. So when we add the two of them, that's just congruent to 1 plus 2, which is equal to 3. 2137 minus 512 is congruent to 1 minus 2, which is equal to minus 1, which is congruent to 5. And their product we saw is 1 times 2, which is equal to 2. We can, because we are working modulo 6, and we often do, become a little lazy perhaps, and just replace all these congruent signs by equality, as long as it's clear from context what is intended. And finally, we have a little bit more notation. When I say 16 mod 7, then that's going to be the same as 2, because 16 is 2 sevens, 14 plus 2. And we sometimes read the 16 reduced modulo 7. And continuing along in that vein, if we say something like the sequence 5, 10, 15, 20 mod 7, then that's the same as the sequence 5, 3, 1, 6 mod 7, which is just 5, 3, 1, 6, because 5 is 5, 10 is equal to 3, 15 is equal to 1 mod 7, and 20 is equal to 6. And as I mentioned before, sometimes instead of writing 27 is congruent to 6 mod 7, we'll just write 27 is equal to 6 mod 7. In the last slide, we saw some examples where we did calculations modulo 6, and we saw that we could replace one integer by another if the two of them were congruent modulo 6. A similar result is true in general, and it's probably worthwhile writing it out a little bit more carefully as a practice in formulating a theorem properly and as an example of how we structure a proof, a rather simple one in this case. So the general result is that if you have two integers, a1 and a2, which are congruent modulo n for some fixed n, and b1 and b2 are similarly congruent, then a1 plus b1 will be congruent to a2 plus b2 modulo n, and likewise their product, a1 b1 and a2 b2 will both be congruent, and also a1 minus b1 is congruent to a2 minus b2. That doesn't actually require a new proof, because when we subtract b1 from a1, we're really multiplying b1 by minus 1. And so we can apply the multiplication result, and then we're adding that to a1. So subtraction, a minus b is just a plus minus 1 times b. So to write out the proof, we, as usual, write down the information that we can assume, which in this case is a1 is congruent to a2, b1 is congruent to b2, or modulo n. Now if we write out what that really means, then we have that a1 is a multiple of n, q1 times n, plus r, and a2 is a multiple of n plus r. the multiples Q1 and Q2 are not necessarily the same, but the n is the same and the r is the same. And similarly, for B1 will be some multiple of n plus t, and B2 will be some other multiple of n plus t, where r is bigger than or equal to 0 and less than n, and similarly for t. So now, just adding up, it follows that A1 plus B1 must be Q1 plus S1 times n. We've just added those terms. And likewise, if we add these terms, we get r plus t. So the whole result here is congruent to r plus t, because this here is just a multiple of n, and so it can be ignored when we're working modulo n. And similarly, A2 plus B2 is equal to r plus t modulo n. And so that proves the result. A1 plus B1 must be congruent to A2 plus B2. Remember, we're always working modulo n here. So the same proof goes through for subtraction, or also, as I mentioned before, it's a consequence of the result for multiplication, multiply by minus 1 in this case, and addition. Finally, the proof of the result for multiplication is again similar. So if we multiply A1 and B1 using these two expressions here, we're going to get Q1 S1 times n squared, so that's multiplying these two. And likewise, if we multiply that, and likewise that one and that one, we're going to get multiples of n. So we will get Q1t plus S1r, that's Q1t plus S1r times n, plus the fourth term in the cross multiplication would be RT here. And these terms here are all multiples of n, so the result is just RT. It's congruent to RT modulo n. And similarly, exactly the same argument shows that A2, B2 is congruent to RT modulo n. So that means that A1, B1 and A2, B2 are congruent modulo n. And so that's the end of the proof. And it's probably just worth remarking that there's no strictly analogous result if we're going to use division, because the problem is that A1 over B1 is not an integer. One could formulate a result for division in case, as it turns out, that n is prime, but it's not really worth the effort.